Today we are going to be learning about circular functions, which you can see from the screen here, that those are the word for trig functions that have the units in radians instead of degrees. Now, the reason they get a special name is because circular functions are way more useful than trig functions with degrees as the units in modeling things. In other words, doing word problems that have trig type patterns going on. So remember, we've talked about where we see trig functions in the real world. Anything that kind of goes up and back down and up again, like the temperature during the day, right? It gets, it's cold in the middle of the night and then the sun comes up, it warms up, warms up, warms up until it's the end of the afternoon. It's as hot as it's going to be, and then it goes back down, right? So that is, an example of something that has a sinusoidal pattern, and if we wanted to model it with an equation, we would need to use radians instead of degrees in our units. So that's not really what we're going to focus on today, that word problem aspect, but I am going to just talk to you about how can I graph circular functions when I have radians instead of degrees as the units. So one thing I want to point out here is that, if I just look at this equation, right, this one here, it's kind of hard to tell whether this is an equation that it is in degrees or in radians. So there's a couple of clues. One is that it has a pi in it. That is a clue that this is probably going to be in radians. But there's a better way that we are going to use as a convention in this class. And I want to be really clear that this is a convention for this class only. When you leave UPrep and you go on to your life as a mathematician at an exotic university, like I know all of you are going to do, this is not something that everybody is going to be in agreement with you on. They'd probably not have learned this. But we are going to say that when we use x as the independent variable instead of theta, that is going to be convention that we're going to use when that the x is in radians. In fact, even when you get to calculus next year, people are going to use theta and they're going to mean stuff in radians. But here in pre-calc, just for ease of use, we're going to say x means radians, theta means degrees. Sweet. Okay, so how do I graph this if it says x and it has pi in it and I know that it's in radians? Pretty much exactly the same way that you graphed a sinusoid that was in degrees. There's a couple changes, but it's more or less exactly the same thing. Let's think about the outside transformations, the things that affect y. That doesn't make any difference if you have degrees or radians, right? The input to this function is what's in degrees or radians. The output is still going to be a sine ratio. How that changes is not going to have any effect on what units the input is in. So these two numbers, -4 and 6, do exactly what they used to, right? So -4, this is the sinusoidal axis, and 6, this is the amplitude. Okay, so I'm going to go ahead and draw my axes on. It looks like the sinusoidal axis is -4, so I'm going to make sure I have lots of room at the bottom part of my graph. I'm going to go ahead and draw my axes like this. And I'm going to have everything go up by 2's to make sure that I fit everything on the graph. Okay, and I know that the middle of the graph is going to be at -4, so I'm going to draw a nice dotted line here, and that the top of the graph is going to be at -4 plus 6, which is 2. And the bottom of the graph is going to be at -4 minus 6, which is -10. Okay, so now I've started off this graph exactly the same way I did before. Now, here comes the tricky part where it matters that we're in radians instead of degrees. Okay, now what we always did before to figure out the period, so in degrees, what we did was we said the period was 360 divided by b. Now that doesn't make any sense to do anymore because the period has nothing to do with 360 anymore. 360 is a number that is inherently dependent on degrees. And where did that 360 come from? This was the natural period of sine and cosine. Okay, so 360 was the natural period of sine and cosine, in degrees, right? But the natural period of sine and cosine in radians is, it is 2 pi. Okay, so what was 360 divided by b about? Why did that give us the period? Well, this pi over 12 number here, right? This is 1 over the dilation factor, right? In other words, if I flip that fraction and I get 12 over pi, which if we think about it, that's about 4, right? That's telling me how many times narrower or wider this graph is getting. So 12 over pi is about 4. This graph is going to be about 4 times as wide as it was before. It's not, I don't want to think about it, and actually say, oh, I'm going to do 2 pi times 4. What am I going to do to get the actual period? I'm going to do 2 pi times 12 over pi, right? So if I think about it, this is the natural period. And this is the dilation factor. So this is equal to 24. So this is saying that it's going to take 24 units to complete one full cycle of this sinusoid. Exactly like a period is always meant before. But now I figured out that this is the period. So in general, I'm going to make a note over here. In general, what I can do to figure out the period is, instead of doing 360 divided by b, I can do 2 pi over b. Now that I'm in radians, because 360 degrees is the same thing as 2 pi radians. Huh, that's not that hard. Okay, so my period is 24, and I know that this number here is still my phase shift, or my phase displacement. In other words, remember that if I have x plus 9, that means the phase is actually minus 9. So d is minus 9 for this graph. Okay, so now I'm going to have to take all this information, put it together, and figure out how to put the graph on exactly the way that I did before. If I want to figure out a really good scale for this, I can still do exactly what I did before when I was in degrees and look at the quarter period and compare it to the phase shift, right? The quarter period is 24 over 4, which is 6. So if I look for the biggest common factor between 6 and 9, that's going to give me a great scale. So I'm going to go ahead and label that on here. I'm going to say that every square is 3. Challenging at the moment to add 3 so many times. This is probably the most exciting part of the podcast ever, huh? Now I'm totally, I screwed something up, didn't I? Yeah, these aren't multiples of 3. Oh, over here. Crap. Okay, I'm going to pause this and fix it. Be right. Okay, I'm back, and magically the scales appeared. Okay, so now I actually want to put the first point on this graph. So if the quarter period is 6 and the phase is -9, I'm going to put that first point on by going to the phase displacement -9, and I'm going to put the first point on the graph. I'm going to decide what critical point I have by the type of graph I have. This is a plus sign graph, so that first critical point is going to be in the middle on the way up. That's where the first point is because it's a plus sign graph and the phase is -9. And then every quarter period, so every 6 units, I'm going to get another critical point. So the next critical point is going to be at the top. 6 units later, right? 6 units later, I'm going to be back at the middle. 6 units later, I'm going to be at the bottom. Middle, top, middle, bottom, middle, top, middle. Okay, no more room. And now I'm just going to connect the dots with a nice smooth line. Ta-da! There's our sinusoid. It's really not that much different than it was before. Let's take a look at one other circular function problem. So this is a slightly different one. It's going to be a little bit harder for us to figure out the scale, but let's just start with what we know. Okay, so I know that the sinusoidal axis is 5 and the phase or the amplitude is 7. So I'm going to go ahead and put my vertical scale on here. Randomly put this in here. If my midline is at 5, I probably want to make sure that I have lots of room above the graph. So I'm going to go ahead and put my axes here, and I think I'm going to go up by 2s, even though this is odd because my graph isn't that big. 6, 8, 10, 12, 14, -2. So my midline is at 5. My top is at 5 plus 7, which is 12. My bottom is at 5 minus 7, which is negative 2. Okay, super. Okay, now I want to figure out the horizontal scale and the horizontal, what's going on in the horizontal axis. So I'm going to figure out the period. Okay, the period is 2 pi over b, just like it used to be 360 divided by b. But here, b is 4. It's not a number with pi in it like I had last time, so that it was super convenient and the pi is canceled out. Here, I get 2 pi over 4, which is the same thing as pi over 2. Huh. Okay, so my period is pi over 2. So this is saying every pi over 2 radians, I complete a full cycle. Huh. So it's probably going to be convenient for me to label my x-axis in terms of pi. We'll get to talking about that in a second. Let's look at the phase first. My phase displacement is pi over 16, right? That's d. So that's saying that at a value of, oops, 16, not 6, a value of pi over 16 radians is where I'm going to put my first critical point on this graph. Okay, so do you see that my phase displacement and my period, which are the two things that are having to do with the x-axis, are both in terms of pi? So I can figure out the quarter period, right, the same way that I did before, and I get, you know, pi over 2, which is my period, divided by 4, which is pi over 8. So that's telling me that every pi over 8 units, I'm going to get a critical point. So if I look at my quarter period and my phase shift, I want to pick the greatest number that goes into both of those evenly, thinking about in terms of pi. So it's obvious to me, it might not be obvious to you, that the right choice is pi over 16. Right? If I think about it, 1/16 is half as big as 1/8, right? So pi over 16 is half as big as pi over 8. So I'm going to go up by pi over 16s. So this is where it gets a little bit tricky because you have to be a fraction genius, right? So 2 pi over 16, you can just label 2 pi over 16, but you can also recognize that 2 pi over 16 is the same thing as 8, right? 3 pi over 16, 3 and 16 don't cancel, so that's 9. 4 pi over 16, though, that's pi over 4. 5 pi over 16 doesn't cancel. 6 pi over 16, I can divide a 2 in the top and the bottom, so I get 3 pi over 8. 7 pi over 16. 8 pi over 16 is pi over 2. You kind of see what's going on. So what I'm going to do now is just, I'm not going to label every one now because I'm a little bit lazy. So I'm just going to do the ones that are multiples of 8. So this is going to be 5 pi over 8. I'm going to skip the next one. 6 pi over 8 would be 3 pi over 2. Skip the next one. This is going to be 7 pi over 8. And then the next one is going to be pi. 8 pi over 8, right? Okay, so now that was a pain. I'm not going to lie, that was a pain. But really the hard part is over now, and I treat this graph exactly the same way that I did before when I was putting the points on. I just had to deal with this annoying labeling the x-axis part of the program. So when I go to the phase shift value, pi over 16, I'm going to put that first point on. This is a minus cosine graph, so that first critical point that I put on the graph at pi over 16 is going to be at the bottom. And then every pi over 8, which on this graph is 2 squares, I'm going to get a next critical point. So from the bottom, 2 squares later, which is pi over 8 later, I'm going to be at the middle. The next one, I'm going to be at the top. 2 more, I'm in the middle. 2 more, I'm at the bottom. 2 more, I'm in the middle. 2 more, I'm at the top. See what I'm doing? And I'm going to go backwards a little bit too. Okay, and now I'm just going to connect the dots. And a nice smooth, I kind of missed that one, but you'll forgive me. Nice smooth sinusoid. Okay, so there you have it. 2 examples of sinusoids. Circular functions being graphed. We can have circular functions in terms of tangent and secant and cosecant and cotangent as well. Those are obviously going to be a little bit more challenging, just like, you know, in degrees, tangent and cotangent and secant and cosecant were a little bit more challenging than sine and cosine, but it's the same exact process for those graphs as it is for these. The only thing that changes is the natural period of the graph is no longer pi, or it was no longer 360, and now it's 2 pi. That's all there is.